and I did my PhD at H2ase Kolkata with Professor Abhishek there. Today, I'll be presenting my PhD work only, which is on oxygen-tolerant hydrogen production and hydrogen oxidation by iron-iron hydrogenase model complexes. So before I start, I want to thank to the organizing committee, especially Gustav, for inviting me and giving me the opportunity to present my work in front of hydrogenase community. I'll be very quick in the introduction part as I'm presenting in front of hydrogenase community. So hydrogenases are the enzyme of which catalyzes the oxidation, which catalyzes the oxidation of hydrogen to proton reversibly at near thermodynamic potential. These are found at lower organism in deep ocean where the oxygen level is very low. Based on metal ion composition, they have been classified in 3 different classes like nickel iron, iron, and iron only hydrogenases. Today I'll be talking about iron hydrogenases only. Okay. So this is the active site structure of iron hydrogenase. This is the Fe2S2 substrate, and this is the Fe4S4 cluster, which act as an electron shuttle. And this is the vacant site where proton substrates like protons or hydrogen comes and bind. This is the reactivity cycle of iron hydrogenases. This forward is the hydrogen oxidation cycle, and the reverse is the proton reduction cycle. But the major problem is when we expose the iron hydrogenase enzyme to air, it results irreversible degradation of the catalyst and permanent loss of the catalytic activity. So investigating the deactivation pathway of iron hydrogenases in presence of air is an active field of research. Initial Xmas analysis with the enzyme suggested that the reactive oxygen species which generated upon exposure to air destroys the Fe4S4 cluster, which stops the electron shuttle and permanently damaging the HAR activity. Later, a theoretical investigation suggested that the reactive oxygen species generated may oxidize the Fe2H2 substrate, Fe4S4 cluster, or any of the sulfur atoms present in the H cluster. Later, studies of electrocatalytic oxygen reduction by synthetic model complexes from our group indicated that the formation of RO species is mainly degrades the Fe2S2 substrate upon oxygen reduction through sulfur oxygenation. So for this study, they took these 3 different complexes. Among these 3, 2 of them having DZ nitrogen and the other without DZ nitrogen. When they plot the percent of prose formation with pH, they observe that after a certain pH, like pH after pH 4, the prose formation decreases, and at pH 0, the prose formation is minimum around 25% or even lower in case of these 2 complexes. While in case of this complex, the prose formation is more than 45% even at pH 0. So this indicates that there must be a important role of DZ nitrogen atom. They have also proposed the mechanistic cycle of oxygen reduction by this kind of synthetic complexes, and they proposed that during oxygen reduction, this kind of hydroperoxide intermediate is involved, which gets stabilized by this kind of hydrogen bonding. So the question is, can we design and synthesize a model complex with higher basicity at the nitrogen center so that we can increase the extent of hydrogen bonding to stabilize this hydroperoxide intermediate and selectively cleave the O bond to form the benign water, which is no longer harmful for the cluster. So keeping all this information in my mind, I have designed and synthesized a series of 2 aryl substituted iron hydrogenase model complexes. And these are the early reported 4 aryl substituted model complexes. When we compare the solid state crystal structures of these two complexes, we observe that in case of 2 aryl substituted one, the CNC plane and the phenyl plane are almost perpendicular to each other. While in case of 4 substituted one, the CNC plane and the aromatic plane are almost coplanar to each other. Then we wanted to know the solution phase structure of these complexes. For that, we performed proton NMR in CDCl3, and we observed that in case of 2-ethyl substituted one, the methylene peak appears at the upwell region compared to the 4 substituted one. And this can be explained in this way that in case of 4 substituted one, as the CNC plane and the phenyl plane are almost coplanar to each other, the nitrogen lone pair can delocalize into the aromatic ring. And hence, there is a development of partial positive charge. For that, this CH2 peak appears towards downfill region. While in case of 2 substituted one, this kind of resonance is not possible, and instead the nitrogen lone pair is localized on no localized. So we can say that this kind of complexes has higher pKa compared to the 4 substituted one. Next, we wanted to compare the HCl activity of these complexes. For that, we performed linear voltammograms in anaerobic 100 millimolar KPF6 aqueous solution under heterogeneous condition, and we observed that in case of these 3 complexes, a large catalytic current over the here. But we do not see any significant current, catalytic current in case of these 2 complexes. Then to determine the in situ product formation, we perform rotating ring disk electrochemistry experiment. This is the ring disk setup. This black part is the working electrode. Here we use is plain graphite electrode. And this white part which encircles the working electrode is the platinum ring electrode. So during RRD experiment, we fixed the platinum ring potential at a particular value for a particular pH so that it can oxidize hydrogen at the platinum ring. And from this platinum ring current, we confirm that this current is due to the hydrogen production. We have also confirmed the hydrogen production by GCT-CD. So from this, we have determined the over potential of hydrogen reduction reaction, which is around 160 to 180 millivolt, which is very low compared to the early reported complexes. And also the turnover frequency is fairly high compared to the early reported complexes. So the high turnover number and low over potential could be explained in this way that in case of 2 aryl substituted one, the nitrogen lone pair is well oriented towards one of the metal centers, and this is protonated at this pH. So after metal hydride formation, it immediately takes the proton to form molecular hydrogen, just like Dubai catalyst, where the nitrogen lone pairs are well oriented towards the metal center. Then we wanted to know whether our catalysts are stable in presence of air or not. So to do so, we perform rotating ring disk electrochemistry experiment in aerobic 100 millimolar KPF6 aqueous electrolytic solution. First, we fixed the platinum ring potential at 0.7 volt, where it can oxidize both the H2O2 and H2 produced at the working electrode. And we observed that in case of these 2 complexes, a large platinum ring current over here. But we do see a small platinum ring current over here in case of these 3 complexes. But when we fixed the platinum ring potential at 0.5 volt, where it could only oxidize hydrogen to proton, we do not observe any platinum ring current for this complex, but we observe a small platinum ring current over here in case of these 3 complexes. So from these results, we can say that the large platinum ring current over here is due to the H2O2 oxidation, which is forming due to partial reduction of oxygen by these 2 complexes. And the platinum ring current over here and there is due to the hydrogen oxidation, which produced at the working electrode with these 3 complexes. Next, we performed bulk electrolysis experiment at minus 0.7 volt in aerobic aqueous solution, and we observed that in case of 2 array substituted one, the periodic yield of each year is more than 70%, and the prose formation is less than 4%. While in case of the post-substituted one, the prose formation is more than 50%, and the periodic yield of each year is less than 15%. So this results indicates that the enhanced pK of the BZ nitrogen can facilitate the protons transfer and diminishes the prose formation. Also, the selective reduction of oxygen to water can increases the selectivity as well as stability of the model complexes. Now, an interesting feature was observed when we performed cyclic voltammetry with this complex instead of linear sweep voltammetry. When we perform CV, we observe a periodic process at 155 millivolts. And when we shift the potential to more negative, we observe that the periodic current increases. But when we stop the potential before the HCR process, we do not observe any periodic current over this region, which indicates that the periodic process at this potential is associated with the cathodic one. Then we performed a bulk electrolysis experiment at minus 0.8 volt, where it could produce hydrogen, and followed by LSVs. And we see that with the increasing time of bulk electrolysis, the periodic current at this potential also increases. Then, when we rotate the electrode right after the bulk electrolysis, we do not observe any current over this region, which indicates that the hydrogen which is produced in situ is oxidized by the same complex on the electrode surface. So to further confirm that, we performed linear sweep voltammetry in presence of different hydrogen concentration, and we observed that the catalytic peak current increases linearly with the partial pressure of hydrogen, which indicate first order kinetics with respect to hydrogen concentration. Then we performed hydrogen oxidation in organic medium, and we observed that the catalytic current increases linearly with the increasing base concentration, as well as with the square root of partial pressure of hydrogen, which indicates that the hydrogen oxidation in organic medium is first order with respect to base concentration as well as hydrogen concentration. Next, to determine the periodic efficiency, we have performed a bulk electrolysis experiment in hydrogen saturated deuterated acetonitrile medium in presence of excess diisopropyl ethylamine and followed by proton NMR. And we observed that the peak around 4.53 ppm, which decreases with the increasing time of bulk electrolysis, is due to the dissolved hydrogen in acetonitrile medium. And the new peak, which arises and increases with the increasing time of bulk electrolysis, is due to the formation of diisopropyl ethyl ammonium salt. And integrating this area, we have determined the periodic efficiency of hydrogen oxidation, which is around 82%. And the turnover number is around 200 after 10 hours of electrolysis. Then for some mechanistic studies, we performed time dissolved FTIR with complex 1 after adding excess cobaltation and malonic acid. And we observed that after 5 seconds to 50 minutes, these three peaks gradually decreases along with the appearance of 4 new peaks at these frequencies, which indicates the 50 to 70 millivolt red shapes of these three initial IR band indicates that the Fe2S2 cluster is reduced by 1 electron. So in presence of malonic acid and excess reductant, the stretching frequencies matches with the early reported 1 electron reduced protonated species, which is reported by the Lomoff and co-workers in 2019 in their chemical science paper. Then we performed the IR spectroscopy, FTIR, in presence with complex 1 after addition of excess cobaltocin and malonic acid. And you observe the 4 new band over here, which matches with the 1H species, which is 1 electron reduced protonated species. DFT calculation also support the formation of this 1H species. And also we have a Mosbauer data, which also supports the formation of 1H species. Next, based on the experimental data and DFT calculation, we proposed the mechanistic cycle for hydrogen production and hydrogen oxidation. And it is like the complex 1 first reduced by 1 electron and proton to form this in protonated reduced species, which again reduced by 1 electron in presence of proton to form this mixed valent in protonated iron hydride species, which is energetically uphill by 29 kilocalorie per mole. And then this hydride and the proton combines together. Okay, I should mention this, like the Beijing hydride species and the terminal hydride species are almost thermoneutral in our case. Okay, next, the hydride and the proton combines together to form this molecular hydrogen, and in eliminating the hydrogen, complete the catalytic cycle. So in conclusion, we can say that we have designed and synthesized a new class of iron-iron hydrogenase model complexes, which can reduce proton to hydrogen at low over potential, even in presence of oxygen, that is oxygen tolerant HAR. And this class of complexes, model complexes, can also oxidize hydrogen under heterogeneous and homogeneous conditions. So a bifunctional kind of catalyst. We have also characterized the 1 electron reduced protonated species by spectroscopic technique. Finally, I want to acknowledge my supervisor, Professor Abhishek De, Ma'am Somdota Ghosde, and the entire Day group, all my collaborators around the world, and all the funding agencies for providing us money. And finally, all of you for your kind attention.